Hello. In this video, I'm combining exercises 6.3.1 and 6.3.2 from Broverman, modified version of them. I'm going to use algebra and calculus to explore the graphical relationships between term structures, which are yield curves that come from spot rates, and what we've been talking about recently, forward rates. As you can see, this video is pretty long. It's pretty challenging conceptually speaking. As always, when I do long, challenging conceptual videos, I really hope that you get a lot out of it. There's a lot of content here, so you're going to want to roll up your sleeves and have some paper, get ready to pause the video and check my calculations and really think about what I say. It's got a lot of parts to it here, 7 parts, A, B, C, D, E, and F. We'll take them one at a time, but I will say before I start here that parts A through D I'm going to do on the paper here. And parts E and F, I'm going to use a computer program called Mathematica that you don't have to understand, but it's going to allow me to help you understand how to interpret some things here. It's got some nice features that will be pretty neat, I think. Okay, let's again just take it step by step. Let's read through the problem here. Suppose we are given a term structure, in other words, essentially a yield curve, a bunch of spot rates. Think of these as being R1, R2, R3, R4, etc. Okay, those are interest rates on zero coupon bonds that are in effect at the present time. And let's go ahead and think about part A here. In fact, part A, there's really nothing to do because I'm going to use what I did in video number 145. I'm not going to rederive it. We're going to write an expression for the forward rate in effect from time k minus 1 to time k in terms of the spot rates, the RTs. Could call those RKs, but this is the way the book wrote it. Again, this was derived in video 145, so I'm not going to rederive it. But if you don't know much about spot rates, term structures, and forward rates, you are going to want to watch some of these preceding videos before this one, okay, to try to understand that. So the formula for part A, I'm going to do more than just write it down. I'm going to write it in a few different ways because these different ways will be helpful in doing the other parts of this problem. The formula for the forward rate in effect from time k minus 1 to time k. In terms of the term structure here is 1 plus the spot rate RK, which is the effective annual yield on a zero coupon bond for say k years, to the kth power divided by 1 plus R sub k minus 1 to the k minus 1 power, all minus 1. Okay, what are forward rates? I'll briefly remind you how to interpret them. There's really 2 ways to interpret them. Based on a given term structure, you can think of these as being your estimates for rates that are going to be in effect in the future. Another way to view them is as, well, at the present time, you can enter into contractual obligations, fancy financial products, where you can guarantee that you get these forward rates in future years. Okay, that's the formula. A couple other ways to write this formula that will be helpful in this video. We can write this fraction here as a product, 1 plus rk to the kth power times 1 plus r sub k minus 1 to the negative, in parentheses, k minus 1 power, then minus 1. I also could distribute that minus sign through the parentheses there. I could write a minus k plus 1 as well. One other way I can write this that will be helpful is I can take one of those factors of 1 plus rk and put it out in front, 1 plus rk to the first power, and then with what remains in the fraction, write it as a single fraction to the k minus 1 power, where I have 1 plus rk on top and 1 plus rk minus 1 on the bottom. Then don't forget to subtract 1. Okay? A couple alternative formulas for this forward rate that will be handy as we continue in this problem. All right, that's part A. I didn't derive it. In this video, you can see video 145 to see the derivation of that. Part B. Show that this equation is true. Okay, now technically speaking, to do this as a formal proof, I should use mathematical induction. Okay, I'm not going to do that here. That's kind of beside the point. We want to just see the idea of where this formula comes from, and then we'll make use of it. Well, try to understand what it means. And in fact, I can briefly describe what it means here. But before doing so, I should say that this formula right down here is only valid when k is greater than or equal to 2. when k equals 2, we would be talking about the forward rate in effect from year 1 to year 2. But you see a forward rate here in effect from year 0 to year 1, from time 0 to time 1. That really is the same as the first spot rate, R1. Okay, that's understood here. As far as understanding what this tells you, you can use this formula to think of 1 plus RK by taking the kth root of both sides is the geometric mean of these numbers, 1 plus f from 0 to 1, 1 plus f from 1 to 2, etc., 1 plus f from k minus 1 to time k. 1 plus f01, 1 plus f12, etc. What's a geometric mean, you ask? Well, I'm not going to get into it. You can look it up. It's not the same thing as an arithmetic mean, which is an average, okay? But it can be interpreted somewhat like an average, especially when these values are close together, okay? And we'll see how to interpret that visually when we get onto the second part when we use Mathematica. Anyway, as far as showing that, again, I'm not going to do a formal proof of it, but as far as understanding why it's true, let's go ahead and take this thing on the left-hand side of this equation and go ahead and plug in the formulas for these various forward rates. Again, f sub 0 to 1, meaning the forward rate in effect from time 0 to time 1, is really the same as R1. So I can replace f01 with R1. 1 plus f12, I can use this formula, add 1 to both sides, and I really get this expression right here with k equal to 2. What will that equal? It will equal 1 plus R2 squared over 1 plus R1 to the first power. And you can see right away the 1 plus R1s will cancel. Next one would be 1 plus the forward rate in effect from time 2 to time 3. So k would be 3 in that case. I can use this formula again, add 1 to both sides, and what I would get this expression right here with k equal to 3. That would be 1 plus R3 cubed over 1 plus R2 squared, and the 1 plus R2 squares will cancel. You can see the pattern start to emerge here. The next one would be 1 plus R4 to the 4th over 1 plus R3 cubed, etc. The second to last term in this product, when you would have a k minus 1 right there, would be 1 plus r k minus 1 to the k minus 1 power divided by 1 plus r k minus 2 to the k minus 2 power. And finally, the very last expression, the one you actually see here, which can be found by adding 1 to both sides of this equation and getting this expression right there, would be 1 plus rk to the kth power divided by 1 plus rk minus 1 to the k minus 1 power. And again, as you can see, a bunch of stuff cancels. This cancels with this cancels with this cancels with this cancels with the next denominator, etc. This one's going to cancel with something that comes before it. This cancels with this. Everything cancels except for this. And you're left with 1 plus rk to the kth power. And again, if you take the kth root of both sides, like I mentioned up here, that really means that 1 plus rk can be interpreted as something called the geometric mean of these other factors here, these growth factors that come from the forward rates. All right, on to part C. Part C, show that these derivatives, this derivative and this derivative, are positive and negative respectively. And that's where, well, at least with the second one, where this formula is going to come in handy, this version of the formula. Key point here before I go ahead and take these derivatives, I'm not thinking of k as a variable when I do this. I'm thinking of k as fixed. I'm thinking of rk and rk minus 1, which are in the formula for fk, as the variables, okay? So it's a little bit of a strange perspective to kind of have. I'm not differentiating with respect to k, and in fact k is an integer, 1, 2, 3, 4, 5, 6, etc. I'm thinking of the entire expression rk and the entire expression r sub k minus 1 as being variables when I take the derivatives here. Okay, so we use the formula for part C here. Take the derivative of this thing with respect to rk. I treat the rk minus 1 as a constant. I'm also treating k as a constant. This is really a power function minus 1 of rk, or of 1 plus rk at least. I can use the power rule. This is just a constant down here. I would have to bring the k as a constant. I'd have to bring the k in front, get k times 1 plus rk. I'd have to subtract 1 from the exponent, get a k minus 1 power over 1 plus rk minus 1 to the k minus 1. That's just a constant with respect to rk as well. And then when I differentiate minus 1, I get 0. So this is the derivative, and all these quantities are positive. The r's technically can be negative. You can have negative interest rates, but they have to be bigger than negative 1. So 1 plus these interest rates are going to be positive. K is positive here. This whole thing is definitely positive because its constituent parts are positive as well. Okay, and k effectively is bigger than 2 here, and so k minus 1 is going to be greater than or equal to 1. No problem there. All right, what about the derivative with respect to rk minus 1? That's where this form of the formula comes in handy. Again, think of k as fixed. Also think of rk now as fixed. The variable now for the second derivative is, not a second derivative, but this second one that I'm doing is rk minus 1. So this is a constant, it just stays there, 1 plus rk to the k. This is a power function of 1 plus rk minus 1, where the power is this negative quantity up here. I can bring that down in front of it, get negative k minus 1. I can also bring that in front if I want to reduce the number of parentheses here. And then I have 1 plus rk minus 1 to the negative k minus 1 minus 1, subtract 1 from the exponent. And then when I differentiate minus 1, I get 0. If you like, this can be simplified. Distribute the minus sign through. I get a plus 1, then a minus 1. The 1s would cancel. This would simplify to negative k. This is positive, but this thing right here is negative. And so the whole thing is negative. Okay? So there we have verify those derivatives. We will be interpreting the meaning of this. If you look down here in parts E and F, when I use Mathematica, I will be interpreting what I see for part E here with some particular examples. In light of parts C and D, these derivative facts and what I'm about to show in part D, I'll be doing graphical interpretations of those things. We'll be thinking about what that really means. All right, on to part D. Show that if rk is greater than rk minus 1, if the next spot rate is greater than the preceding spot rate, or if this is true for all k, in other words, the yield curve is increasing like it is usually in real life, then the forward rate from time k minus 1 to time k is greater than the spot rate rk. And again, remind yourself what the spot rates represent, at least the way we're thinking of it. rk represents an effective annual yield on a zero coupon bond with term k years. This forward rate is going to be greater than that. Okay, which sounds like a good thing, and it could be a good thing for your investments. Okay, show that if this is true, then this is true. That's going to be where this form of the formula comes in handy. So assuming rk is greater than rk minus 1, that's going to imply that 1 plus rk is greater than 1 plus rk minus 1, just by adding 1 to both sides of the inequality. And that will imply, if you divide both sides by this, which is not a negative number, that 1 plus rk over 1 plus rk minus 1 is greater than 1. Okay? Hopefully you can see where this is going. That's going to imply this thing's bigger than 1, and this whole thing is bigger than 1 plus rk, and then the 1s would cancel. Let's go ahead and write that down now. The forward rate from time k minus 1 to time k equals 1 plus rk times the fraction 1 plus rk over 1 plus rk minus 1, all to the k minus 1 power minus 1. That's going to be bigger than 1 plus rk times 1. Up here I could say that this is going to be, when I raise this thing to the k minus 1 power, it's also going to be bigger than 1. Minus 1. The 1's will cancel here. That cancels with that. You're left with rk, and we have verified what we wanted to verify. The forward rate in effect from time k minus 1 to time k is bigger than the spot rate rk. Okay, so we're about now to go into the Mathematica, but before we do, maybe let's just look at parts E and F and to see what we're about to do. We're about to consider two particular yield curves, term structures, is another name for that, lists of spot rates. You can make graphs of these things. Two particular examples for k going from 1 to 12. Actually, in Broverman, k just goes from 1 to 10, but I thought it was a little bit more interesting for the second example, especially to let k go out to 12. Again, we'll be using a computer program, Mathematica, to calculate the corresponding forward rates, and we'll make tables of values. We'll plot those forward rates along with the yield curves and compare. And finally, the most important part is the interpretation. Interpret the results of part E for these two examples in light of parts C and D, including situations where I allow with Mathematica R9 and R10. I could have picked R11 and R12, but I thought I'd pick R9 and R10 to see some other effects, are allowed to increase in value while holding the other spot rates fixed. That's going to be relevant for thinking about these derivatives there. Okay, so now let's go to Mathematica. All right, now we're on to the Mathematica portion of this video. We're going to consider parts E and F of this problem. Actually, in making this Mathematica notebook that you see here, I decided I wanted to even do a little bit more at the very end, but that'll come later. You don't need to know Mathematica to appreciate what I'm going to show you here. We're going to focus on some concepts with some graphs. You can just appreciate the main ideas and try to understand them. If you happen to have Mathematica or want to learn Mathematica, you can also pause the video and copy down the code if you like. We're going to consider two examples, two yield curves, in other words, term structures, one that's linear, this first one, and a second one that's quadratic. As k goes from 1 to 12, actually in the textbook, k only goes out to 10, but it turns out to be a little bit more interesting, especially in the second example, to let k go out to 12 because it's nonlinear and it ends up being an increasing function at first and then decreasing. To distinguish between these, I'm going to call this one R1 sub k and this one R2 sub k. Again, we're going to use Mathematica to calculate corresponding forward rates based on these term structures and plot these forward rates along with the yield curves, which are really the graphs of these things. We're going to graph them in a discrete way just when k is a positive integer. And then part F, the most important part, we're going to interpret the results that we see from part E in lights of parts C and D, which I'll remind you of when we get there from the first part of the video, including situations where R9 and R10 are allowed to increase in value while holding other spot rates fixed. I could have picked R11 and R12, but I decided I wanted to pick R9 and R10 because we're going to see that R11 and R12 are, well, they're unaffected by R9 and R12 is unaffected by R10, but you'll see what I mean when we get there. So here are the yield curves themselves. This is code that will enter these functions into Mathematica, and here are the corresponding forward rates. Effectively, I'm using a shorthand notation f sub k in place of f sub the interval from k minus 1 to k. This is the forward rate in effect for that time interval. Anyway, these are piecewise functions. You could recognize the formula for the forward rate in general here, although in the situation where k is 1, you've got to make sure it's the same as r1. All right, here's Mathematica code that will generate the data. You don't have to worry about that. We're more interested in the graphs. Well, this is the actual data itself here. We are ultimately going to get to the graphs here in a minute. So what we see here is tables of values. You've got the different values of k, 1 through 12 in both cases, the first case and the second case. The first example is the linear example, the second example is the quadratic example. We're seeing the values of the spot rates, in other words, the term structure here. If I graph it, it's the yield curve in both examples, and these are the corresponding forward rates that are calculated by the formula as they should be. You can notice that the forward rates in both cases are bigger than the corresponding spot rates, except in the second case, because that's where the graph of the term structure, the yield curve, ends up decreasing at the very end. These forward rates down here actually end up being less than these spot rates right here. Okay, if you want to pause the video and write these down if you're interested, if you're taking this class with Broberman's book, the 7th edition, you could write these numbers down if you want. All right, now more importantly, let's go on to the basic plots, and we can try to interpret this fact from part D. So I'm reminding you of what part D here is. When r sub k is bigger than r sub k minus 1, when the next spot rate is bigger than the preceding one, or you could interpret this as being true for all k, meaning the yield curve is increasing, the forward rates are going to be bigger than the corresponding spot rate. And we can see that with the graphs here. So what we have here is a graph of both examples. The first example on the left, the second example on the right. This first example you can see is linear, the second one is nonlinear. You've got the spot rates, the yield curve in the red dots here in both cases, and then you've got the corresponding forward rates with the blue dots in both cases. And again, with k equal to 1, they were equal, so you can see the blue dot is a little smaller than the red dot, so that when k equals 1 here and here, you can see that they are the same point. But then the forward rates here are higher than the spot rates because this one is always increasing. That's an increasing yield curve. Over here, when the red graph is increasing, the blue graph is higher, except now when over here, when k is 11 and 12, the red graph starts decreasing, and so the blue graph goes lower. Okay, so that's an interpretation, at least in the increasing case, of this fact. That's relatively easy to interpret. Let's go down here now and go to the second thing to interpret for part, let's see, that was part D. I think this was part C, though I didn't label it. Let me go ahead and label it here, part C of the problem. We want to interpret these derivatives. Again, these are a little harder to interpret. What's really going on here in both cases is you want to think of k as being fixed, and you want to think of the spot rates themselves, r sub k or r sub k minus 1, changing, and you're seeing how those things affect the forward rate from time k minus 1 to time k. This derivative with respect to the entire variable r sub k is fixed, it's r sub k, that's the variable. That derivative is positive, so if I increase r sub k, the forward rate there should increase. And this one is negative. If I increase r sub k minus 1, the preceding spot rate, the forward rate should decrease. Okay, this is complicated looking Mathematica code that will allow me to do this in a nice way, to actually make an animation that will allow me to change r sub 9 and r sub 10 in both the first example on the left and the second example on the right, and see what happens. So let me go ahead and open up these sliders. We can see the values of our R9 and R10 in the first example, and then R9 and R10 in the second example are set here. They're set to be what they should be based on the original formula. But these sliders in Mathematica now allow me to change these numbers. I can increase R9 for the first example. What should we see? We should see, coming down to this graph, when k equals 9 right there, the red graph, which is the value of R9, should go up. Okay, and then the question is, how does that affect the blue graph? So let's see what happens here. As I increase R9, look at the graph on the left, we see that some sort of change is happening. The blue graph is being more affected. Small changes in the red graph are having a great effect on the blue graph. Those derivatives are somewhat large, you might say. But I am increasing the R9 value. You see that f from the interval from 8 to 9, which is the output of the blue graph right there, is higher, and f over the interval from 9 to 10 is lower, consistent with the fact that the derivative here is positive and the derivative here is negative. In this case, k was 9. This is the forward rate from time 8 to time 9 then is going to be increasing because this derivative is positive. And then over here, when we think about k minus 1 being 9, this would be the forward rate from time 9 to time 10. That derivative is negative. That one goes down. Okay, well, that's what we see here. Whoops. All right, let's go back up. This is having trouble here. Let's go back and put R9 back to where it started. And you also see that the other forward rates, the blue dots, are not affected by changes in R9. What if I change R10? Now look at the graph down again. Now we see the red dot above k equals 10 going up, and the blue dot above k equals 10 is going up, and the blue dot above k equals 11 is going down. Okay, just like before. Okay, I really could have just changed one of these, but I chose to set it up to change both. The same kind of thing should happen with this graph over here. R9 and R10 changing. We should see the blue dots over here changing in the same kind of way we saw before. Second example now, look on the right. Now the red dot above k equals 9 is increasing, the blue dot above k equals 9 is increasing, and the blue dot above k equals 10 is decreasing. And if I shift it over by changing R10, essentially the behavior just shifts over by 1. Now I'm changing R10. You can see the blue dot above k equals 10 going up and the blue dot above k equals 11 going down. Okay? So both of these dynamically illustrate these facts. That's a way to help you interpret it. All right, so that pretty much sums up the main content of the video, but I do want to show you a couple extra things that I thought of before that I originally thought about doing this. I want to give you, first of all, an alternative interpretation of these derivative facts, and secondly, remind you of the fact that I said in the first part of the video that really 1 plus rk is what's called the geometric mean of those things. It turns out to be less than or equal to the ordinary arithmetic mean when you add the numbers up and divide by how many there are. Though you'll see in what I show you here that the values of the geometric mean and arithmetic mean are very close together. All right, how about this alternative interpretation of this? This involves multivariable calculus, essentially. What I've got here is I'm thinking of the forward rate as being a function of two variables. I'm calling rk minus 1 and rk, and this is the formula for the forward rate that we've seen in general. It's a function now of two variables, although k I'm treating as a parameter that I can change in this manipulate animation down here. So I can enter this function and I can plot it, and there it's plotted. What is this showing us? Okay, if you've had multivariable calculus, this should seem familiar, and if you haven't had it, well, I'm going to try to help you understand what it's showing us here. This is showing us the output of this function for different values of r sub k minus 1 and r sub k. If I hover the cursor over these different lines here, you see different numbers. Those are the values of those forward rates. When k equals 2, I can make k equal 3 or 4, 5, 6, etc. What this graph is called a contour map. These lines that are probably not exactly lines, but they're close to being lines, are called level curves. They are values where they are curves where the function is constant. Okay, and the constant values are given by what you see there with the numbers like that 0.198 right there. Lighter shading corresponds to higher values for the function. Darker shading down here you can see a negative value corresponds to lower values for the function. Why do I have this green line in here? That's the 45-degree line. When you're above that green line, rk is bigger than rk minus 1. When you're below the green line, rk minus 1 is bigger than rk. It's really the above the green line case that's the typical case. Usually in real life, yield curves are increasing, and so rk would be in general bigger than rk minus 1. And so what we're seeing here is that when in that kind of typical case, you're going to typically have higher forward rates. That's what we see here. Whereas we're down here, we can have lower forward rates like this one, 7.7%, or even negative forward rates, negative 6.6% down there. What about the derivative facts again? Well, that can be visualized by imagining either moving to the right or upward in this diagram. If I start at a certain point, let's say I start here where r sub k minus 1 is, if you go straight down, about 0.10, and r sub k, if you go straight to the left, is about 0.13. You can see the value of the forward rate there is about 16.5%. If I move to the right, if rk minus 1 increases while rk stays constant, the values of the function go down. Okay, that's reflective of the fact that this derivative here is negative. Rk minus 1 is increasing, the values of the function is going down, so that derivative is negative. On the other hand, if I go upward in this diagram, the value of the function goes higher. You can see the outputs are going higher to like 22% there. As rk increases while rk minus 1 is held constant, the function values increase. That's reflective of the fact that this derivative is positive. And that happens no matter where you are in this diagram. Though it's interesting, the graph does change for higher values of k. That is reflecting the fact that those derivatives on the function values are different for higher values of k. In fact, more extreme, you can see this is 76.8% there for the forward rate from time 8 to time 9, it looks like it would be when k is 9. And these are more extreme negatively as well, negative 48% there. So that's another way you can visualize what this means. Finally, let's remind you of this fact here again, that 1 plus rk by the formula that we thought about in the first part of the video is really this product to the 1 over k power, which means the kth root of that product. It's called the geometric mean of those numbers, which is always less than or equal to the arithmetic mean. That can be proved. The arithmetic mean is the ordinary kind of mean where you add up the numbers and divide by how many there are. And this code here is going to allow us to visualize this. It's kind of complicated looking code to create this graph here. Actually, I think I didn't need all of that, but oh well. This is the graph that we're after here. This is the nonlinear example. You can see the red graph. That's, again, the yield curve. It's increasing and then decreasing slightly at the end. The blue graph is the forward rates going up, then down, and it's always higher than the red graph until k equals 11 and 12. Anyway, what this is illustrating is that the value of 1 plus R4, actually I should also tell you, I forgot to say, that this is not really the yield curve, it's the yield curve shifted up by 1. I've added 1 to everything. You can see these numbers are above 1. This is 1 plus R4. You can see it's the second coordinate of this point right here, above k equals 4. It's the geometric mean of these blue numbers that correspond to the second coordinates of the first 4 points here, 1 plus this forward rate, 1 plus this forward rate, 1 plus this forward rate, and 1 plus this forward rate, the second coordinates of those first 4 blue points. 1 plus R4 is the arithmetic average of those, the geometric mean. The arithmetic average I calculated turns out to be right here. It seems like they're pretty much the same thing. Are they really the same thing? Not quite. Let's see. If you calculate the, let's see, it's this number right here. No, got the wrong number there. If you calculate, where is it here? This one. The numerical value of 1 plus R4. I guess I don't want to do a plus 1 there. It's about 1.0964. That's the value of the red arrow there. Okay? If you calculate the mean, the arithmetic mean, and get a numerical approximation for that, you can see it's practically the same thing, but it is ever so slightly higher. Okay? So the green arrow, the point I'm trying to make is the green arrow is not equal to where the red arrow is. It is ever so slightly higher. The geometric mean is slightly less than or equal to the arithmetic mean. The differences sometimes can be larger, but with these numbers, it's not much of a difference. Thank you for sticking with me through the whole video. I hope you got a lot out of this.